all the classes of all the subjects of the master are recorded in Teams. So later, if you want, you can review any part of the class that you are interested on. This is the first session of a subject which is called high performance tools. Okay, so I'm going to share the syllabus, a kind of syllabus from the subject here. Before we start with the contents of the subject, I would like to tell you about how this master is. This master is taught for you that are here in Coruña with me in the classroom. There are people also in Santiago that are in a remote location, but from a classroom in a university. And then we have also several people that are at home or at work in different parts in Spain, or maybe outside of Spain. Okay, so the idea is that I have to teach the class sat down. I don't usually teach the class like this because it's quite uncomfortable for you, for me. But this is the best setup that we have for remote teaching. So I have to write with my pencil here in the screen. So I'm not going to use the whiteboard, although we have one here. We made several tests with that, but it didn't work properly. Okay, so that's the way the class is going to go. First, I would like to tell you about the main contents of the subject. If you were yesterday in the presentation of the master, probably Jorge gave you an overview of the master. So the idea of high performance computer is that wherever you have high computational demands, you need to make some effort in order to speed up one application, okay? And you are going to do that in two different ways. With the hardware, the idea is that you are going to use not a regular computer, but a supercomputer, something like that, or at least a good computer with lots of memory and a good GPU, a good graphic card. But if you, okay, maybe somebody's trying to enter. Okay, sorry for the interruption. And then in order to exploit the resources of that supercomputer or cluster or very good computer, you need to do some kind of parallel programming, or at least to be able to exploit somehow the high performance capability of the computer. So this subject that we are starting today is an optative subject within the master. And the idea is that it's like a transversal subject where you are going to learn how to evaluate the performance of one application, how to detect which are the main hotspots of one application. The hotspot is the part of a program where you spend most of the execution time, okay? Because usually when you have a big program with hundreds of thousands of lines of code, you will realize that you spend, I don't know, 60% or 70% of the execution time in a few loops, okay? Like 100 lines of code or so, okay? So the first thing that you have to do is to be able to detect those hot spots of the application in order to be able to focus your interest or your efforts in those parts of the code where it's more challenging to speed up the application. And also, you need to be able to understand why the performance in that part of the application is so bad, okay? Obviously, in other subjects like heterogeneous programming or parallel programming, you are going to learn how to use parallel programming skills in order to create programs that can exploit a supercomputer or a multi-core processor or something like that. Okay, but here we are going to focus more or less in the diagnosis, okay, of the application, to be able to understand why the performance is so bad and what can we do in order to improve the performance of that application. Okay, so today we are going to have 4 hours of class. I don't intend to be 4 hours here, okay? This is not my intention. Actually, this classroom is all full for September because it's too hot, okay? So maybe we will spend here like 2 hours or 2 hours and a half, and then you will have time to continue with your work on your own, okay? In another location or here. If you want to stay here for 2 more hours, you can do it, okay? Or you can do it in another part of the building. I will be available for you for the last 2 hours, okay, in my office, and you can contact me by email or by Teams. I don't know if everybody here has access to Teams. No? So it's very urgent that you talk to Jorge Gonzalez, which is the coordinator of the master, in order to enter into the Teams platform, because we are going to have everything available there, including these meetings and the recordings of these meetings, okay, and all the stuff of the master. Okay, so today we are going to talk about an introduction to the subject, and we are going to cover some basic concepts of high-performance computing, okay? We are going to talk about high-performance architecture and also some basic concepts of performance metrics, like how, for instance, if you want to say how fast is a car, maybe you are going to say that the peak speed is 200 kilometers per second, no, per hour, or something like that, okay? So which kind of metrics do we have in computers in order to assess or to evaluate the performance of a computer? And at the end of this presentation of today, we are going to cover some of the fields, some of the areas where you are going to be able to apply high-performance computing successfully, because it's necessary to apply it, and because many people is currently using high-performance computing in those areas, okay? This is going to be my first class. You are going to have 4 more classes with me, but I'm going to disappear for 3 weeks or something like that. And then the other teacher, Emilio José Padrón González, is going to come later, starting next week, and he is going to cover the main course of the subject. Okay, and he's going to tell you for 2 classes about the compiler. Okay, the compiler is the tool that you have already used, probably in other degrees or studies that you had before, that is able to translate a program that is written in a high-level language into machine code, okay? But in addition to that, this compiler is able and can optimize the code for you, okay? Probably if you do nothing special with the compiler, you will notice, or you will notice that this is happening actually. The compiler is optimizing your code, is saying something stupid human. You wrote this that is terrible for the performance of the computer. I'm going to improve it, okay? And he's doing that for you. But with Emilio, you're going to learn to have a better control of the optimization process of the compiler. And you're going to be able to instruct the compiler to optimize further your code, okay? And this is going to be an important capability, because you will experience yourself that using certain flags when you call to the compiler, you will speed up your application for free, okay? Just doing that, just passing some flags to the compiler. Also, we are going to cover some topics about compilation, generation, and deployment of HPC software. The idea is which tools are required in order to make your software portable, your HPC software, okay? Probably you have downloaded several times applications, I mean source code from applications from the internet, and you attempt to compile it in your own computer, or maybe to reproduce some results in your own computer, and you were not able to do it, or maybe yes, okay? So you are going to learn in this part of the subject how to make this process easier for the person that downloads your software, okay? And finally, for 24 hours, this is 6 classes, we are going to learn to use tools for measuring, characterizing, and representing the performance of an application in a computer, okay? And we are going to see 2 different worlds. The world of open source, okay? So we are going to see free open source tools, but we are going to make also agreement with the devil, okay? And we are going to see also tools from Intel, okay? Intel is one of the main providers of hardware, specifically of processors, and they have a big set of tools that allows you to diagnose and improve the performance of your application. We are going to learn how to use this set of tools. Okay. Regarding the evaluation of the subject, you know that here in Spain the evaluation is of a total of 10 points. Okay, so 30% is going to go for the final exam. We will have this exam online in Aula Fesga in January. The date is already fixed, okay, in advance, and you can use your notes, okay, or any kind of material in order to do this test. The 70 remaining percent of the evaluation is going to go for a supervised project. This project is going to be like a running project that you are going to do throughout the course, and it can be done individually or in pairs, okay? It's up to you to decide how you want to do it. Obviously, we advise you to do it in pairs because this way we have less things to correct, okay? But that's the only idea, because you are so many students this year in this subject, okay? So we need to simplify our work. Okay, and we are going to have 3 different deliveries, okay? The first task is going to be proposed today. You will see that this is extremely simple task, okay? It's just like a warm up, okay, in order to start the course. And then second and third task are going to be proposed more or less in day number 3 and day number 6, okay? And they are a bit more challenging, okay? The idea of this project, the overall idea of this project, is that you experience the process between you have the idea to implement something as a high-performance computing software. You make your first version of this software, and then you try to optimize it in different ways, okay? First with the compiler, and that's up to the part of the subject where we are going to talk about the compiler, and then later on we are going to see all these open source and Intel tools that allows you to diagnose your application, okay? Any questions about this? Because this is the end of the syllabus. No.
¿Las preguntas se pueden hacer en castellano?
Yes, no problem with that. We understand Spanish. The teachers.
¿Es necesario aprobar ambas partes por separado?
No, there is not a minimum required for passing. Actually, you can have a 0 in the final exam and a 7 in the supervised project. But that will be extremely rare. I mean, it's not usual to have 100% of the project and then to do nothing in the final exam, okay? But it can happen. If it happens,
se escucha un poco distorsionado. No sé si es por la mascarilla, por el micrófono, pero ayer en la charla inicial se oía con mejor calidad, yo creo. ¿Os pasa lo que...
What about now?
Mejor, mejor.
Okay, so I'm going to change the location of the microphone. Okay, so let's start then with the introduction to the subject. So, as I told you before, in this first talk about the subject, we are going to make a small introduction. I'm going to divide this class into two halves, okay? The first half, we are going to talk about some basic concepts that are required in order to be able to go through the course, okay? Like basic concepts of computer architecture or computer structure, okay? Maybe most of you already know these concepts, okay, so sorry about that, but we believe that it's important that at least we devote 1 hour or so to go or to review these topics. And after that, we are going to have a small break, okay, in order to drink some water and go to the bathroom. And then we are going to have the second half where we are going to talk about different fields or different environments where we can apply high performance computing, okay? This is just some kind of motivation for you in order to understand in how many areas you can apply this superpower that you are going to acquire in this master, okay, which is high performance computing. Okay, so okay, this is the outline. That is basically what I told you before, and let's start from the beginning. Okay, so this is the von Neumann, or at least a representation of the main building blocks of the von Neumann architecture. This represents a computer, but obviously schematically, a computer is not something like this at all. So this part here is the processor, or the CPU, the central processing unit. The main purpose of the CPU or the processor is to execute instructions on data, okay? So in order to do this, we need, on one side, registers. These registers are buffers or locations where we can store information, namely the data on which we want to perform the different operations, and obviously the places where we are going to store the results, and also the codification of the instructions that we are executing, okay? In order to perform different operations, we need something that are called arithmetic logic units. The idea of arithmetic logic units is that they can perform different kind of arithmetic logic operations, okay? So if you want to make an addition, you are going to have one of these units that is able to add two numbers, two floating point numbers or two integer numbers. It depends on the situation, okay? And then it's going to store the result in a third register. In order to control the operation of the processor, we need something that is called the control unit, okay? Nothing interesting. As you can see here, this part of the processor, this part of the chip of the processor, requires to communicate with the rest of the computer, and specifically with the memory of the computer, to exchange the codification of the instructions that is going to execute and the data on which the operations or the instructions are going to be executed. And obviously, once these calculations are done, sometimes it's going to send this information back to the main memory. Okay, that's the idea. So the memory itself, although here is represented as a monolithic single device, is not something like this. And we are going to see it right now. The memory is divided in different devices. For instance, within the chip of the processor, when we buy a processor, we also buy something that is called the cache memory. And this is part of the chip of the processor. In the motherboard, we usually have pinned something that is called the main memory, that is usually sold in modules, in memory modules. Okay? And then below that, we have the input-output system, where we connect things like the graphic processing unit or the hard drives. Okay? Okay, so the processor. This is a representation, also a schematic representation of the operation of the processor. So the basic idea is that we get one instruction that we are going to execute on one or several pieces of data. Okay? And the idea is that both instructions and data are taken from memory. Okay? And the result sometimes is sent back to the memory. Okay, but later we will see that this is not the usual scenario. In a CPU, in a processor, normally we are going to be executing all the time, concurrently, several instructions on several pieces of data at the same time. And this is something that we are going to call parallelism. Okay? So probably this master, if it was not called master in HPC, should be called master in parallelism. Okay? Because this is something that we are going to try to do all the time, to parallelize things. Okay? To do several things of the same kind at the same time. Okay, so returning to the memory subsystem, the memory subsystem, as I said before, is composed of a set of small devices, okay? And is usually represented in computer architecture books like a pyramid or a hierarchy, okay? This is a pyramid, Egyptian or Mayan pyramid. And the idea is that in the peak of the pyramid, we are going to have very small memories, very expensive, and by expensive I mean that the cost per byte of information is very high with respect to other types of memory, and very fast. Okay? Actually, in the peak of this hierarchy, the speed of the memory device matches the speed of the processor. Okay? As we descend in the memory hierarchy, we are going to have slower devices, okay? Larger devices with more capacity, and also cheaper devices, okay? Meaning, again, that cheaper is that the cost per byte is becoming lower and lower, okay? So here, what we have is the cache. Did you know of the existence of the cache memory? Yes? Okay.
Yeah.
When you buy a chip of a processor, inside the chip of the processor, you open a computer. In the motherboard, in the center of the motherboard, more to the top left, you have pinned the chip of the processor. Inside the chip of the processor, there is a small memory which is called the cache memory. And it's a very fast, very small, and very expensive memory, okay, that we are using in our computers all the time. And it's also a volatile memory. You know what it means? That everything that is in there goes away when the power goes away, okay, when the power is off. So below the cache memory, we have something that is called the RAM memory. Okay, probably most of you already knew of the existence of the RAM memory. Okay, is available in your phone, in your smartphone, for instance, or in any kind of other computer. Below the RAM memory, we have usually the secondary storage, okay, or also known as the hard drive. And this is a non-volatile device where we store all the information that we want to make permanent, okay, that we don't want to go away when the power goes off. Okay, so that's the idea of the computer memory hierarchy. And I would like to show you how different can be this between a CPU and a GPU, okay? Some of you are going to have two different subjects.
¿Soy yo o se ha parado?
No, definitivamente
se ha parado. Pensaba que era mi internet.
Se ha caído el profe, parece, ¿no?
Sí, creo que es cosa del Teams en Linux.
Oye, yo creo que estamos aquí todos que hablamos en español, ¿no? Creo.
Sí, creo que sí.
No, la mayoría. Hay uno que ha escrito en el chat en inglés.
No, joder, pues...
No, ese es español, lo conozco yo.
La verdad que no tenía ni idea de que la clase de hoy, de que esto era una clase que se iba a dar. Pensaba que era una presentación. ¿Vosotros sabíais algo?
Yo tenía pensado que sería una presentación por cómo solía ser en el grado y tal, pero en cuanto he visto un mensaje por el Teams, que han pasado el tema, han pasado una práctica y todo, he dicho, vamos a ver, vamos a calmarnos.
Joder, parece que hay...
Yo ya me lo esperaba.
Y entonces, ¿sabéis si las clases van a ser así? ¿Estaremos así conectados por convocatoria así, aquí te pillo, aquí te mato, de estas inmediatas? ¿O esto se queda grabado de alguna forma? ¿O sabéis cómo va?
A ver, grabarse se graba, lo están grabando y luego se va a subir al Teams. Pero sí, yo creo que es así, en plan, pasan la convocatoria por el Teams y te metes directamente. Sé que parece poco profesional, pero realmente es más cómodo.
Ya, lo que pasa, no sé si habéis entrado en el aula CESGA. Yo acabo de entrar ahora mismo y parece que es un Moodle o algo así parecido, que tiene asignaturas creadas. Y vamos, no hay documentos ni nada ahí.
A ver, hay horarios de las semanas.
Hello?
Universidad también.
Can you hear me?
Hola.
Yes.
Okay.
Yes.
Okay, so we are going to continue now. Sorry, I don't know what happened, but Teams kicked me out of the meeting. Okay, so let's share the screen again. It's still recording, so no problem with that. Okay, so the idea of the memory hierarchy is that we are going to have faster memories in the topmost levels of the memory hierarchy, which are smaller but also very expensive regarding the cost per byte. Okay, And as we descend in the memory hierarchy, the memory is becoming slower, but also larger, but also cheaper. Okay? So what's, yes? ROM memory. Read-only memory, you mean? Because you see something? No, ROM memory is the acronym of ROM read-only memory. But this is usually in the BIOS, for instance, something that you don't want to write. Okay? But RAM memory is random access memory. And the idea of okay. In the case of random access memory, it's just superconductors technology that is usually used for implementing the RAM memory. Okay, but the RAM memory is not here. It's not part of this hierarchy. Okay, it's something more rare. Okay, so what I was saying before we rested the connection is that the memory hierarchy can be slightly different depending on your device. In a CPU, and this is a very old sample of CPU because we have only 2 cores, the idea is that obviously each core has its own registers, and below that there is a hierarchy of cache memories, okay, with different levels of cache memories. The first levels are usually private to each core. This means that each core of the CPU has its own cache memory from the first level. And then the last level is usually shared among all the cores of the CPU. Okay? And after that, we have obviously the RAM memory. In the case of the GPU, and I'm talking about the device that you plug into the PCI Express slot, okay? What you have is a big computer itself, but with lots of small cores, okay? I'm talking about 200, 500, or something like that cores, but simpler than in the case of the CPU, and this is represented here. And obviously, they have a shared set of or bank of register, and then usually what we have is that the levels of cache are shared among several of them, okay, including also the RAM memory, okay. So the idea of this slide is just to show you that depending of the type of architecture, the structure of the memory hierarchy can change, okay? And this is something that you have to be aware of in order to improve the performance of your application. Okay, so this is another sample of cache memory and memory hierarchy. This is a drawing from Emilio, okay? Hand drawing, obviously. And this is a core with 2 levels of cache, which are private to it, and another core, and you can have several of these, like 4, 8, 12, depending on the computer. Then you usually have a shared level 3 of the cache, which is shared among all the cores of the computer, and then you have, in another part of the motherboard, the main memory, okay? Regarding the latency, because something that we said is that when we access something that is in the topmost levels of the memory hierarchy, that is the registers or the different levels of the cache, this is going to happen very fast. The processor is not going to have to wait a lot for the data to be loaded, okay? However, as you descend in the memory hierarchy, you are going to pay more time, you have to wait more, in order to bring this data from memory. And obviously, when you have to go to the hard drive, okay, you have to pay much more time. So this is an idea of more or less how much time you pay depending on to which level of the memory hierarchy you access. So in the case of the register, it's not even measured in terms of time. It's just one cycle of the processor, okay? Because it's instant, okay? It happens at the speed of the processor. When you access to the cache, depending on the level of the cache that you access, you have different latencies, okay? So in the level 1 of the cache, the latency is around 1 nanosecond. Okay, this is just an estimation, and it depends highly of the technology, which means that the processor has to wait between 3 or 4 cycles. Okay, this is not too bad. Okay, this is actually one of the best possible scenarios. When you have to access data in level 2, you have to pay more time because you have to pay 10 cycles, and this is 3 nanoseconds, okay? When you access the level 3 of the cache, you pay even more, and when you access to the main memory, you pay much even more, okay? So obviously, in order to the memory hierarchy to work properly, we need that most of the memory accesses happen at the highest level of the memory hierarchy, okay? But there is a problem with that, and is that in the cache memory, we usually can store a few megabytes of information in total, okay? Like 32 or 20 or something like that. In the RAM memory, depending on your amount of RAM memory that you have, you can store like 16, okay, gigabytes of information. And obviously, below here, you are able to store in the order of terabytes of information, okay? So when you are using a computer, if the computer is working properly, and if the application that you are using is working properly, you are having a smooth experience, okay? You see that things happen smoothly. But you know that when your computer becomes older, but the software becomes newer, and is more computationally demanding, what you experience is that it's very laggy, okay? And the reason for the computer to be laggy can be that the processor is not able to keep the pace of the program, executing instructions, or normally because you access too much information in the lowest levels of the memory hierarchy, okay? So in order for this to work properly, you need to exploit something that is called the locality, okay? Yes?
What do you mean by cycle?
Cycle is, the processor is a synchronous machine. So it has an internal clock that it makes like some kind of tic-tac, no? So when you buy a processor, they usually tells you the frequency of the processor is 2.2 gigahertz, okay? So this is giving you how many cycles, in this case is 2.2 billions of cycles per second, gigahertz means that, okay? So one cycle is just one of these cycles, of these tic-tacs of the clock, okay?
And can we have more than 3 cache memory, or?
No, it's not usual. I have never seen any platform that has more than 3 levels of cache. It's a standard.
And less than 4, can we have?
Less than 3, yes. That happens. For instance, in GPUs, it still is quite common to have just 2 levels. And until 10 years ago, or something like that, it was normal to have just 2 levels. But in the last 15 years, 3 levels has become like a standard. I don't know why. Maybe because manufacturers have experienced that this is the optimal situation. Okay? Okay, so in order to make this work, we need that most of the memory access happen in the topmost levels of the memory hierarchy. And in order to do this, or in order to have this, we need to exploit something that is called locality. Do you know this concept from any previous subject? Something like that? Okay, the idea of locality is that when you load information in a computer, when the computer starts, all the information is in the permanent storage, in the solid state drive, in the hard disk drive, whatever, okay? And as we start the computer, at the beginning, you know that the computer takes some seconds to start, okay? And the reason is that it's executing things in the processor, and at the same time, it's populating the volatile levels of the memory hierarchy with useful information. So every time you require a piece of data, you are going to load not just that piece of data, but also more pieces of data which are near that one, okay, like a block of information, okay? And this is happening in the registers, in the cache, and in the main memory, okay? So once you have done so, there are 2 principles. The first one is that it's called temporal locality, and says that when you access a piece of data, it's very likely that this piece of data will be accessed anytime soon. Okay? You can think on this at the program level. When you start Chrome, the browser, okay, you are using all the time the browser. So if you access information from a website, this information is brought from the internet, is loaded into the main memory, the cache memory, and finally is shown to you somehow, okay? But obviously, you don't jump from one website to the other, okay? So this is called temporal locality, okay? At the program level, in the program, you have structures that you are doing computation over and over on the same pieces of data. For instance, you can have something like this within a loop. Okay, this is a for each loop, and obviously you are accessing all the time this x value. Okay, so this is called temporal locality, and you can see that it works at the low-level program, okay, but also works at the conceptual level. Okay, I mean, when you use something in the computer, it's very likely that you use that something soon. Okay, so it's important to keep that information in the topmost levels of the memory hierarchy, because next time, as it's very likely that you need it later, it's going to be already there. Okay? The spatial locality says that when you access a piece of data, it's very likely that you access pieces of data that are nearby that one. Okay? And that works, for instance, at the top level. If you think that you are accessing a big file, and this file is stored in the computer, in the hard drive, in a sequential location, so you are going to load this information sequentially. Okay? So when you bring a block of information, you are going to load information that is going to be required anytime soon. Okay? And this works also at the code level, okay? Because when you access A0 in a program, it's very likely that in the future you are going to need A1, A2, A3, etc. And that's the reason why the memory hierarchy works. Okay, so one of the problems of modern application is that some of them have a very poor locality, and you have to study if that happens, how to prevent it. Okay, so something that you are going to learn not only in this subject but also in other subjects of this master is how to improve the locality of your program. For instance, here we are going to see tools or to use tools that allows you to say or to see if the locality of your program is good or bad. And if it is bad, it's going to tell you this access is very bad because it's jumping in the memory. Like if you have something like A0, then A100, then A200, this is terrible for the performance of the computer. Okay? And this is something that you have to rewrite somehow in order to avoid it. If you can, okay, you don't always can. Okay, so this is just a representation of temporal and spatial locality. Okay? Okay, so this was just a small introduction to computer architecture, just the basics that you need in order to start with the subject. And now we are going to see some basic concepts of parallel computer. Okay? So the first thing that we have to see is the different kinds of parallelism that we can find in a computer. I told you before that if this master was not the master in HPC, will be the master of parallelism. Okay, so we have to understand at which levels of the computation. Okay, this parallelism is possible. The first level of parallelism is the bit level parallelism. This is something that you are not going to exploit yourself as programmer, okay, because it's something that is encoded inside the hardware of the computer. The computer is able to do the same logical operation on different bits at the same time, okay? Nothing else. If you were an electronic engineering, probably you will be more interested in this, okay? Starting here, this is going to be very interesting for us. One of the things that is going to be interesting inside the processor is what is called instruction level parallelism. When we saw the caricature before of a computer, at the beginning we said we have one instruction on one piece of data, and this is what the computer does, okay? But obviously, this is not happening. Modern computers are able to execute several instructions at the same time, all the time. They are able to execute something that is instruction level parallelism, okay? The ability to execute several instructions at the same time. Also, we have something that is called data level parallelism. And this is a type of parallelism that we are going to learn to exploit in this subject specifically. All modern processors have a type of instructions, of special instructions that are able to execute the same operation on several pieces of data at the same time. For instance, in the machine set of instructions, in the set of instructions of a machine, we usually have an addition. An addition is written like this, okay? So these are the input registers, and I'm going to take the value, an integer value, for instance, of one register, and add it to the value of another register, and I'm going to store the result of the addition in a third register. This is a regular instruction. But vector instructions that are able to exploit data level parallelism are something like this. add 4, for instance. This instruction is able to do this with 4 pieces of data at the same time. Okay? Imagine the situation that we saw before, this instruction. We are adding x to hy, okay, ai, a value of an array, but we need to add first a0, then a1, a2, and a3. Think in the situation where you have in your instruction set one instruction that is able to execute this addition in groups of 4. So it's able to execute a0, a1, a2, a3 at the same time, and then a5, a6, a7, a8 at the same time, and so on. Okay? So these vector instructions that are able to exploit data parallelism are available in all modern computers, in every modern computers. And they are used all the time because the compiler, between the optimizations that is able to do, they have this kind of, the introduction of this kind of vector instructions. Okay? Emilio is going to tell you more in depth about this. And also, at the topmost level, we have something that is called task level parallelism. Okay? And this works at very different levels. For instance,
I have a question.
Yes.
So you say that you can apply the one operation to several registers at the same time. So each register have a fixed size, no?
Yes, but yes, I was simplifying, but the idea is that instead of having general purpose registers, you have a special set of registers which are called vector registers. So instead of having 32 bits, okay, they can store 4 multiplied by 32, okay, 128. So you load the information with, instead of a load operation, a load 4 operation, and then instead of doing an add operation, you do an add 4.
Okay.
Okay, but you will see that later more in detail. Okay, at this point I was just simplifying because this is just an introduction.
Perfect, thank you.
Okay, you're welcome. Okay, so the last level of parallelism is what is called task level parallelism. And the idea of this is that we are able to execute different tasks at the same time. And this can work at different levels. For instance, if you get this terminal of a computer and you execute the top program, you are going to see all the programs or all the tasks that are being executed by your computer concurrently. Okay, and obviously everything is happening inside the processor. So the processor has the ability to execute several tasks at the same time. But in parallel programming, you are going to learn that you are going to be able to exploit this inside a program. Okay, imagine that you have a situation where you have a program that is very time consuming and you have 12 cores in your processor and you want to make all the cores to work at the same time running your program. Okay, so in order to do this, you need to exploit task level parallelism. Okay, you can order one task to one of the cores, another task to another core, and so on. Okay, and that will be the way you split the job between the cores of the computer. Okay, and then thinking in this idea of how many types of parallelism we can exploit in a computer, is introduced something that is called the Flynn's taxonomy. Yes. Yes.
You talked about parallelism and the fast level parallelism.
Mm.
Is it possible we can be able to make a fusion of the both? I mean, executing a data level parallelism in a functions and use these functions as a task level parallelism. I mean, parallelism something who is parallelism.
So you mean that you want to spread data level parallelism and task level parallelism at the same time?
Yes.
Yes, that's something that you do. Okay, this is just like an abstraction, but you will see that when you learn parallel programming, most of the time, both types of parallelism are going to be mixed, in the sense that, for instance, you have a loop, no, that you want to do, just one moment, something like this, and you want to do the first 100 elements of A to be processed by one task, the next values by another task, and so on. Okay, so you are doing task level parallelism because you are creating different tasks to do different parts of the job, but at the same time you are doing data level parallelism.
Yes, but that means parallelism. Do parallelism on something
Yes.
is who has been parallelism before. So you will have perhaps a problem of serializations.
No, you shouldn't. If you read the program properly, because I don't know if what you mean is that you can have a situation where you use vector instructions
Yes.
on a parallel program.
Yes.
That happens all the time, and it's not a problem.
Making, I don't know, functions who do parallelism on something.
Yes.
And executing these functions, data frame, but you want to parallelism this on this data frame. So,
But with data frame, you are meaning a Python data frame, a pandas data frame.
yes, so that
Yeah.
means doing parallelizations on something who have been parallelism before.
Yes, but the processor is able to manage that.
Okay.
I mean, actually, not in parallel programming, but in advanced parallel programming, that is another optative subject of the master, you learn how to mix MPI, that is something that you are going to use in parallel programming, with OpenMP, that is another technology. And you can use both technologies and both runtimes, which are completely different, at the same time, and it works. And actually, in the second part of this class, we are going to see samples of software, normally weather forecasting software, that use all the power of the computer like this. Like I have a big supercomputer, and I use MPI to send parts of the job to different nodes of the supercomputer, and inside the supercomputer, the node of the supercomputer, use another parallelization technology to make this work in parallel also within the node. And even within the core, you have vector instruction that further parallelize that, and it works. The result is correct. Well, the weather forecasting is not a exact science, okay, but it works most of the time. Okay, you're welcome. So, having into account this idea of the different kinds of parallelism that we can have, there is a Flynn taxonomy. You are going to see this taxonomy not only in this subject, but in many other subjects of this master, because it's some basic knowledge that you should have. This was announced in 1966, probably before any parallel computer even exists. Okay, but the idea of this Flynn's taxonomy is that he thought about all the possibilities that there could be according to combining different types of parallelism. So no parallelism is this. You execute one instruction at a time on a single piece of data at a time. Okay, so you go just step by step. This is the anti-HPC. Okay, no HPC at all involved in this case. Multiple instructions on a single piece of data is called MISD, is that you execute several instructions at the same time on a single piece of data. This is not very common. Okay, it's something that it has not become very important in high performance computing. This is the situation where you execute one single instruction on multiple pieces of data at the same time. This is the idea of vector instructions. The add4 that I mentioned before. Okay, this is very common. All modern computers have this kind of SIND instructions, and even in the GPUs, this is more and more important. Actually, when we see some applications of HPC in the second part of today's class, we are going to see that in modern NVIDIA GPUs, they have special SIND instructions specifically designed for artificial intelligence. Okay, these are called tensor cores and are able to do very fast one operation that is very common and very frequent in artificial intelligence. Okay, and then finally we have the full equip, the multiple instructions on multiple data, and this is actually what a modern computer does. It's able to execute several instructions at the same time on multiple data streams at the same time. Okay? Okay, so something related to this is the idea of the SPND model. When you write a parallel program, I don't know if you have any idea of how to write a parallel program. Okay? I don't know if you have a previous experience with parallel programming in the past. No? No? So how do you think that is a parallel program? How do you think that is different from a normal program, a regular program? Do you think that you have like different source code for different cores or something like that?
Just special instructions to let know the CPU what to do?
Yes, that's one type of parallelism, the idea of using special instructions that are able to do several things at the same time. But imagine that you want to parallelize things at a higher level. Okay, and with this I mean that I have a loop and I want to distribute the iterations of this loop between different cores. Because I have 4 and the loop has 100 iterations, and I want to make the first core to do the first 25, the next core, the second one, the next 25, and so on. Okay? How do you think this is written? Do you think I have like 4 versions of the program, one for core 0, one for core 1, another for core 2?
Exactamente, hay una serie de librerías, implementaciones que facilitan todo eso, ¿no?
Yes. Above that, you have abstractions for facilitating parallel programming. But the key question here is just if you believe that you are going to have one single program or you are going to have several programs to write a parallel one. What do you think?
Un programa como tal, ¿no? Un programa que sea...
Sorry, we have one answer before. Later.
You use one single program with if instruction.
One single program that
You use the if instruction according to the number of the loops.
Yes, yes, that's one idea.
Would you go for?
Okay, the person in the remote location.
Tú, que no, a los estudiantes que están presencial no se les escucha muy bien. ¿Puedes repetir la idea que ha dicho?
Yes, he said that inside the same program you can have if statements, no, that decides which part of the loop you are going to execute depending on which core you are. Do you understand it?
Sí, sí, yes.
Okay, and what do you think? That you were talking also before.
Hombre, eso es un poco engorroso, un poco sucio, por así decirlo, ¿no?
Yes, yes, but it's a good starting idea. I mean, if high performance computing didn't exist, this will be one intuition to have, like saying, okay, I want to distribute all the iterations of the loop among a number of cores. So I'm going to create a loop with an if statement that asks myself who I am core 0. Okay, so I'm going to do from 0 to 25. And actually, in the innermost level, in the lowest level, it works like this. Okay, obviously you are going to see in parallel programming and heterogeneous programming that you have convenient abstractions to express that. Okay, but the idea that I wanted to emphasize is that the model that we are going to follow is called single program, multiple data. I mean, you are going to have a single version of the program, and depending on some kind of identifier, is going to decide which part of the computation is going to do. If I am core 0, I have to do from iteration 0 to 25. If I'm core 1, from 25 to 15, and so on. Okay? And this is the most primitive idea of parallel programming. Okay? And this is the way things are going to be implemented. Okay? Actually, when I first studied parallel programming in the computer science degree, okay, in the, I don't know, 1996 or something like that, okay, before you were born, one of the things that were more challenging to understand was that, okay, that I have one single program and several instances of this program were going to be created in different cores or different nodes or whatever, and depending on some kind of identifier, they were going to do a different part of the job. Okay? Okay, so this was the Flynn's taxonomy, that is just an abstraction. As I told you before, this was announced in 1966. They were not computers, almost, and they were not at all parallel computers. Okay, so this was like a abstract and free idea. But how they are realized in real life. SISD will be a computer which is able to exploit just something that is called instruction level parallelism. Okay, it's a computer that is able to execute several instructions at the same time, but at different stages. Okay, it's not really doing real parallelism. Okay, actually, you are completely unlucky because on Friday you are going to have a class with me also, because I'm going to teach you the first classes of high performance architecture. Okay, and we are going to talk about the concept of pipelining. That is not going to be new for some of you. Okay, but this is the concept that modern processors implement in order to be executed to be executing several instructions at the same time. In the case of SIND, that is another category of the French taxonomy, there are several examples. The most exotic is array and vector processors. Okay, they were popular in the 90s or something like that, but they are not popular anymore. Although some rarities, like for instance, the TPUs from Google for artificial intelligence could fall into this category. Okay. Also, as I told you before, all model processors have a special type of vector instructions that are able to do SIND, to execute the same instructions on different pieces of data at the same time. Okay, and then we have GPU or similar approaches that are strongly based on the idea of SIND. I mean, executing the same operation on different arrays at the same time. Although in this case, we are doing something more complex. You can think in something that is very well done by GPUs. For instance, matrix multiplication. Okay? If you want to do a matrix multiplication in parallel, you have to do small matrix multiplications in different cores or in different small processors. So basically you are doing or you are repeating the same operation on different parts of the operands. Okay, that will be the idea. Okay, and finally, you have IND, that is the most evolved form of parallelism. And in this case, we will be talking about one of your computers that is a multi-core processor, so it's able to execute several instructions on different pieces of data at the same time, or even a cluster or a supercomputer. Okay, so something that is also very important is how is this programmed. Okay, so for instance, in a monoprocessor with SND capabilities, you can use vector instructions just instructing the compiler to do so. Okay, but you can also do your own programming using this kind of extensions, although this is not very common. Okay, you can also optimize the memory access. In the case of shared memory multiprocessors, this will be something like what you have in your laptop or in your smartphone. What you have are several cores that share the same memory space. Okay, so when I access a piece of data, I don't have to wonder myself if that piece of data is in this node or is on a remote node, because everything is in the same computer. Okay, so you will see when you learn parallel programming that this is much more easier to codify, okay, to encode. And actually, you are going to learn in parallel programming a technology which is called OpenMP, okay? And the idea of OpenMP is that as you have all the data in the same computer, this is something that you don't have to be concerned of, okay? Because you don't need to worry about that. And this is going to simplify a lot parallel programming. However, when you have a supercomputer or a cluster where you have different computers interconnected with a high bandwidth interconnection network, then you need to use a technology normally which is called message passing libraries. Okay, and actually MPI, which is the most popular one, is the one that you are going to learn in parallel programming. And this is going to be learned in the second half of this subject because it's more difficult. Okay, why? Because in this case, as not all the information is in the same location, then you need to explicitly distribute the information among the nodes that are going to do the work. Okay? Okay, so in this master, you are going to use this almost deprecated piece of technology, okay, which is the Finisterrae 2 supercomputer. Okay, in this master, when you see this acronym, F2T, okay, this means Finisterrae. You know what this means, Finistère in French, because Finistère is not in La Bretagne française, it's in Galicia. You know that. Actually, it's a place that you have to visit when you are here. It's 100 kilometers from here. So the idea of this supercomputer, this is the second version of the supercomputer, and actually is almost finished the third version of the Finisterrae. But so far, we have to use Finisterrae 2. Okay? In Finisterrae 2, when you make an SSH connection, you are going to connect to one of the 4 logging nodes. Okay? A big mistake that you are going to do is to try to execute things in the front end, in the logging nodes. This is something that you shouldn't do. Okay? If you do it, something is going to kick you out from the logging nodes. Okay? These nodes are only to enter into this supercomputer and then send jobs or works through a queue to the real supercomputer. Okay? The main part of the real supercomputer are these 306 thin nodes. Okay? Each one of these thin nodes have 128 gigabytes of RAM memory and 2 processors with, I believe, 12 cores each. So each node have like 24 cores. Okay? So when you program something with OpenMP, you are going to submit a work to one of these thin nodes. Okay? And this is going to be executed using the 24 cores available in each one of them. Okay? If you use MPI, instead of using 1, you can use 2, 4, 8, 16, how many, the number you want. Okay, probably there is a limit. I never use more than 32, okay, but you can try. I don't know what is going to happen. There are special nodes, for instance, these ones that have GPUs. There are 2 with special Intel processors, which are called Xeon 5, and there is also one fat node that has 128 cores and 4 terabytes of RAM memory. Okay? So all your information, all your files are going to be available in every node because they have a shared file system that is built with the technology Lustre Parallel File System, okay, where you can store your information. Okay, so we believe that this was a good subject to introduce this idea because you are going to use this facility a lot in the master, okay, so it's good that you know which is the structure. This is the internal structure of each one. Wow, it's blinking. I don't know why. I don't know. Of one of these thin nodes. What you can see is that we have okay, I don't know what happens with this. Yeah. Okay, so the idea is that we have 12 cores in one processor, and as you can see, each core has two levels of cache memory which are private to each core. Remember the concept that we saw before, and a shared level 3 cache memory, okay, for the 12 cores. This will be the second processor with the same structure, 12 cores, two private levels of cache memory to each one, and a shared level in the last level of the cache, okay? These are some technical characteristics of the cache, which are not very relevant. Okay, so to end this part of the presentation, I'm going to talk you or to review some typical performance metrics. For instance, MIPS. In the CPU, we can use MIPS, millions of instructions per second, okay? So in the past, when you wanted to compare two processors, this was something that you were aware of, okay? Like, okay, which one is able to execute more millions of instructions per second? And the one with the higher number, the better, okay? But as you know, nowadays, we have different kind of manufacturers for processors with different technologies, and the complexity of the instructions can be different between different manufacturers, okay? So this metric is not valid anymore to compare two different processors, because sometimes it can be controversial that a computer with a higher MIPS value, when executing, for instance, a matrix multiplication, is actually slower, okay? Because it's doing simpler instructions, so it seems that it's faster according to the MIPS metric, but it's not faster in reality, okay? Because if you measure the execution time of the matrix multiplication, the other instruction is objectively faster. So in order to solve this, something that have more acceptance between manufacturers is the idea of floating point operations, okay? So for instance, if you are doing something like this, in a loop, and this loop has, 100 iterations, you see that if these are floating point numbers, real numbers, you have one addition per iteration, okay? So these are 100 floating point operations, okay, that you have to execute. If this takes you 10 seconds or something like that, if you divide these values, you are able to obtain the flops value, the number of floating point operations that you are able to execute per time unit, okay? And this allows you to compare different platforms for different manufacturers. Actually, when NVIDIA sells you a new car, a new graphic card, they usually tell you that the peak performance is like 2 teraflops, okay? It is giving this metric, okay? And the same happens when Sony is selling a new PlayStation, or Xbox is selling a new, Microsoft is selling a new Xbox. They are telling you the peak performance expressed in flops, okay? Because it's a metric which is accepted by different manufacturers to be a good way to compare different platforms, okay? We will see later that it's not perfect, okay? You can cheat this metric. Another concept that is related to this one is the computational arithmetic intensity, okay? And this is going to be very interesting because sometimes we have applications where we bring a piece of data, we do a single operation on that piece of data, and we do nothing else, okay? So this application has a very low computational intensity, okay? Because it's 1, basically. However, when I have an application where I bring one piece of data, I make 10 or 12 operations on this data, and then that's the end of the computation, this is a high computational intensity, okay? So this value is something that you have to measure in order to understand in which you have to put most of the effort in order to improve the performance of the application, okay? In the computation or in the memory access. If an application has a high computational intensity, probably is not so important the memory performance, okay? Because you are bringing little data and you are doing many operations on this data. So you have to put your effort on improving the computation. In the memory, you have two related concepts. Yes?
En la presentación pone que la unidad de medida es flop partido por byte. ¿A qué se refiere con byte? ¿Los bytes que ocupa un programa en la memoria? No entiendo.
No. It means the flop is the floating point operations, the number, the count. Okay? And byte is the amount of information that you load. So for instance, when you load a single precision floating point number, that will be 4 bytes. Okay? So it's just because you cannot put something like float per element, because the element can have different lengths. It can be 4 bytes, 8 bytes, or something like that. Do you understand it?
Sí, gracias.
Yes, it's just a way to measure it and to make it independent of the length of the data structure, because it can be different. Okay, so also regarding the memory, we have two different values that are important. The latency is the time that takes between you load a piece of data and the first element of that piece of data is brought to you. Okay, when we talk about the memory hierarchy, we said that the latency in the topmost levels of the memory hierarchy were nanoseconds. Okay, 2 nanoseconds or 3 nanoseconds. But also you have a related concept, which is the bandwidth. Okay, that is a metric of throughput or productivity. So how much information you are able to transfer per time unit. So for instance, this applies to the bus that connects a GPU with the computer, which is the transfer speed that can achieve. Because if you have to send 2 gigabytes, it's not the same to do it depending on the size, on the bandwidth of the channel of communication. And finally, in the case of the cache, it's important to know the miss or the hit rate. How many times we access a piece of data and this piece of data was actually in the cache. That we know that it's faster to access it if it is in the cache than if it is not. Okay? Okay, another metric that is important is the speed up, okay? That measures how many times is faster one thing and another. And this is useful in many scenarios. For instance, we have a program, like many that you are going to use in this master, and then you optimize the program because you parallelize it, or you simply use the compiler in order to improve the performance. If you measure the time before the optimization and the time after the optimization, if you divide both of them, this is going to give you an speed up, okay, an acceleration. It tells you how many times faster is the program now after you optimize it, okay? Related to this, there is something that is called the efficiency of the parallelization. when you do something in parallel, for instance, when you start with parallel programming, you are going to do something in OpenMP. So the idea in OpenMP is that you can put to collaborate, for instance, the 24 cores of one node of the Finisterrae 2 supercomputer. So if the time in one node is 100, if you use 2 cores, you will expect to have a time which will be half of the time divided by 2, okay? Because you have 2 cores collaborating in the computation. If that happens, the efficiency is perfect, okay? So this value that you are going to calculate here is perfect. But this is not going to happen most of the time, okay? You are going to get a worse result. But the efficiency tries to measure how good is your parallelization, okay? So if having 2 processors, you get a speed up of 2, this is great, okay? Anything below 2 is not so great. So the efficiency is going to be worse, okay? So this is the idea of this. Okay, we are finishing this first part. So the last thing that I wanted to comment on this part is the idea of strong scaling and weak scaling. So in the example before, you have a program that you parallelize using OpenMP, and then you start to do the test of how good your parallelization is. So you would do this representation. So using 1 core, this is the time that I get. Using 2 cores, I get a smaller time, okay? Using 4 cores, a much smaller time, and so on. So this is called a study of strong scaling. Why? Because the problem size is always the same. So as we put more cores to collaborate, more workers to collaborate, the time is supposed to reduce. However, this is the most obvious idea. However, there is a complementary test that you can do, and it's another way to represent it, and it's weak scaling. In weak scaling, what you do is that when you put 2 cores to collaborate, you double the problem size, okay? In order to try to maintain the execution time constant, okay? When you use 4 cores, you multiply by 4 the problem size, and so on. The idea is that if your parallelization is perfect, you are going to get an almost horizontal time for the execution time, okay? This is just a matter of how you represent it, okay? And what you want to show and you want to prove. Any questions so far? Okay, I exceeded my expected time.
La escalabilidad débil con el tamaño de problema fijo por procesador. Entonces, cuando se incrementa el número de cores, se incrementa el número de datos que se meten en ese programa.
Sí. The idea of this is that, for instance, if you are adding 2 arrays of size 100, if you use 2 cores, you are going to double the size of the arrays. That's the idea, basically.
Vale.
Okay? And in matrix multiplication, for instance, you double the size of the matrices.
Sí.
Okay? Okay. So we are going to make a break here. It's 5:40. We are going to have a break until 6 p.m. Okay? And then we will continue with HPC use cases. Okay? Okay.